Okay, so we'll do the following problem to practice on work of forces. The 10-kilogram block rests on a smooth incline. Whenever they say smooth, so you don't have roughness effects, so no friction acting on your block. If the spring is originally stretched 0.5 meters, determine the total work done by all forces acting on the block when a horizontal force of 400 Newton will push the block up the plane a distance of 2 meters. So, in this problem, we know the total displacement, it's 2 meters. Now, it's very important to read well the given. It's not initially unstretched. Originally, when you started motion, already you had a stretching. So if I name this position 1 and this position 2, then I can say that the stretching of my spring at state 1 is not 0. It's given to be 0.5 meters. So what will be the final stretching at state 2 then? When I want to calculate the work of the spring, I need delta L2. What will be the value of delta L2? If you have a spring stretched 0.5 meters and you stretch it more 2 meters, so in total, your total stretching should consider this value plus the 2 meters, because the stretching is counted from the unstretched legs. So let's say this is L0, okay? You already had a stretching here of 0.5 meters. And now, since you are moving up, you are stretching it more. So you are stretching it an additional 2 meters. So in total, from the unstretched position, you have 0.5 plus 2. So delta L2 will be equal to 2.5 meters. Okay? So now I know the value of delta L1. I know the value of delta L2. So already I can calculate the work of the spring on the block. Okay? So if I represent first, let me represent all forces acting on the block and then determine the work of each force separately. First, we have, of course, the weight which is vertical. Now, since we are moving our block up, so we have a spring force acting on it downward. We have force P, which is applied on the block to lift it upward. We have the normal reaction, which is perpendicular to contact. And since they say it's a smooth incline, so we don't have friction. So our forces are the weight, the normal, and the spring force, in addition to P, of course. So let us start to determine the work of each of these forces on the block. To start with, for the normal, it's perpendicular to the motion. So already we can say that the work of the normal is equal to 0. Now we move to the spring force. We already determined together what are delta L1 and what are delta L2. And here, because I'm interested on the forces on the block, so what will be the work of the spring? I will use the expression we developed together, which is, whenever I consider my system the block, the force of the spring on the block is half K delta L1 square minus half K delta L2 square. K is given, it's 30 Newton per meter. Delta L1, delta L2 were determined. So we said that we replace K by 30 Newton per meter. We replace delta L1 by 0.5. We replace delta L2 by 2.5. Now, you will get a positive or negative result then for the work of the spring?
Positive.
Negative. Why negative? Because delta L1 is smaller than delta L2. Okay.
I thought it's 0.25, sorry.
Yeah, and if we do the interpretation of this, why we got a negative result? It's logical because our block is moving up while the spring is doing on it a force that is downward because it's trying to oppose motion. Okay, so because my spring force is opposing motion, I will expect that the work of the spring will be a negative work, and this is what I got from the formula. Okay, now we still have two forces to determine the work of. We have the work of the weight and the work of P. Now for the weight, as we did in the previous problem, we always have two possibilities. Or we project the weight along motion, so we get a negative projection along motion. And how to get this projection? As usual, the angle with the incline is 30. This means the angle between the vertical and the weight is also 30. So the projection of the weight on motion is W sine 30. And because it's opposing motion, okay, then the work of the weight will be negative. So we can write that the work of the weight is minus W sine 30 times the displacement, which is 2 meters. So times delta S equals to 2. Okay? Now, if we want to use the other method, if you want to use the formula, work of weight is minus W delta Y. We can also use it. Then we should consider what is the vertical displacement of the block. This is the initial position. This is the final position. And this is my delta Y. This is my delta Y. Since I'm moving up, and in this formula, when I put minus, Y is considered positive upward. So this is my Y axis. Because I'm moving upward, delta Y is positive. So, and the value of delta Y is equal to this distance. So I can easily calculate this distance from geometry of my figure, because as you can see, the angle between the incline and the horizontal is known. It's 30 degrees. So this angle is 30. The hypotenuse of this right triangle is my displacement. I had a displacement of 2 meters. So since I know my displacement along the incline and I know the angle between the incline and the horizontal, I can say that my vertical displacement upward is equal to 2 sine of 30. And then if I replace back into my formula, I will get exactly the same result of the previous method. The negative sign will indicate it's a negative work. So it's minus W times 2 sine 30. Which is exactly the same result we obtained with the first method. So until now, the spring is doing a negative work and the weight is doing is negative work. So of course, what will give motion upward is P. So the work of P should be positive and will overcome the negative work of the weight and the negative work of the spring, because they told me that I was able to push the block upward. If my force P was not high enough, then I cannot push it upward. Okay, so I was able to overcome the weight and the spring force. This allowed me to move from rest my block and moving it into the upward direction. So let us verify this. We'll verify what is the work of P. The work of P. So P first, if we look at the figure, is a horizontal force. It's not along motion. This is why the first step will be to project this force along the direction of motion. This is the direction of motion. It's along the incline upward. So if I project P, as you can see, it is along motion. Okay, and to be able to know this projection, I just need this angle here. And this angle is equal to this one. It's equal to 30 degrees. Okay, so if you project P along the incline, you will get P cosine 30. Okay, and now once you have the projection of P on the direction of motion, because it's a constant force and the angle is constant, so you can just say that the work of P is its projection along motion, P cosine 30, times the displacement. Your displacement is 2 meters, so you multiply by 2. And now, after you determine the work of each force separately, you can do the summation of forces, the summation of work of forces, and you will verify that the net balance will be positive. And this was expected because you were able to push your block upward. Okay, so the net work will be the spring work plus the weight work, which is nearly minus 188. And if you compare with the work of P, the work of P is much larger. So the net work will be positive. Okay, any question on this problem? Okay. Let us move now to a new section. We already said that what is the main objective of this chapter? The main objective of this chapter is to relate work to energy. We already developed the expression of the work of forces, and now we'll try to relate the work done by forces on a particle to the change of energy of this particle. And to be able to determine this relation, we should consider first what is all forces acting on the particle. And because we want to relate to motion and energy is related to velocity, if we talk about kinetic energy, of course, okay? And velocity is related to acceleration. So in order to get a relation between work and velocity, I need to pass by the Newton's second law. Because in the Newton's second law, I relate forces acting on my particle to acceleration of my particle, okay? Now, as we mentioned, whenever we have work of forces, the only forces producing work are forces along motion. So any force perpendicular to motion will not do a work. This is why here it's a good idea to work in UNUT frame. Because in UNUT frame, the forces along motion are the tangential forces, and the forces perpendicular to motion are the normal forces. And since we defined work of a force and we know that any normal force will not do any work, then when we want to compute the total work of forces, we'll just have to consider the tangential forces. We don't have to include the normal forces. So now, if I say I just want to determine what is the work of tangential forces, I relate the tangential forces to the tangential acceleration, because I know that sum of tangential forces is equal to the mass times AT. And by definition, what is AT? AT is the change in speed. So AT is dV by dt. But in this problem, okay, I want to try to figure out work. And work will not involve time as we have seen before. Work is relating force to what? To displacement. So to be able to derive a relation between the work and the energy, I should not include the equation of a function of time. I should include the other relations that I know, which is that ATds equals to VdV. In this way, I will include the displacement within my formula. And because I'm interested in AT, I can take ds to the other side. So I can replace in this formula AT by VdV over ds. Once I do this, okay, a good strategy will be to take ds to the other side. Why? Because when I take the s to the other side, what do I obtain? If you look at this expression, I get sum of, I want to consider the summation of forces. So when I take the s to the other side, I have to take sum of ftds equals to mvdv. So by just taking the s to the other side, I get this result. Sum of tangential force times displacement ds is equal to vdv. And this will illustrate for me the work. Why? Because we already said that the work of a force, if a force is along displacement, to get the work, I just multiply the force by the displacement. So since sum of tangential force is along ds, then this term will represent the elementary work of forces for a small displacement. Now, if I want to get the total work, what should I do? I should simply integrate. So let us integrate both sides. Okay? For the first side, what is my variable? For the first side, variable is position. And for the second side, the variable is velocity. So when I integrate ftds between s1 and s2, I will get what? This is the total work, because by definition, integral of a tangential force times the displacement ds will give me total work done on the particle. And when I integrate mvdv, then the integral of v function is v squared over 2. So for the other side, what do I get? I get that the summation of work, all work of forces between 1 and 2 done on my system is equal to half mv2 squared minus half mv1 squared. And we know that the kinetic energy is given by half mv2 squared. So this will represent the kinetic energy at state 2. And this is the kinetic energy at state 1. This is what we call the principle of work and energy, because this principle is relating sum of work of forces done on my system to the variation of kinetic energy in the system. Okay? Yeah.
دكتور يعني نحن نقول the variation of kinetic energy equals to, or the loss of kinetic energy equals to the sum of work.
Yes, total work done by forces on my system. Okay?
Thank you.
Yeah, welcome. Okay, now in the book, in the reference book of this course, Hibbler book, they just use a notation to specify kinetic energy, which is this one. So whenever you see T1, T, this is kinetic energy. You can use what you want, okay? If you are familiar with KE, it's fine for me. But just if you are doing problems in the books or in the solution manual, just to know what is this notation. So this notation is for kinetic energy, okay? So we have demonstrated in the previous slide that sum of work between state 1 and 2 is equal to kinetic energy, or T at state 2 minus T at state 1. So if you take the kinetic energy at state 1 to the other side, you get this form of the principle of work and energy, stating that the initial kinetic energy of the system plus sum of work of all forces acting on the system is equal to the kinetic energy at the final state. Okay? Now, let us consider now, what if we have several particles in the system? Okay, well, not only one particle. Then it's very simple. All we have to do, we can extend the relation to a system of particles. Then we just have to consider sum of kinetic energies at state 1 plus sum of all work of forces between states 1 and 2 equals to summation of kinetic energies at state 2. we'll see that this using a system of particles in work and energy sometimes will be very helpful and will reduce a lot the solution time. We'll see how. So let us do some practice together. Just here in this simple example, they illustrate for you the effect of friction. Okay, so let's say, for example, if I give you a block, I tell you that I give the block an initial speed of v1, okay, and I apply on it a force p. Under the effect of p, the velocity will change, and I want to compute what is the velocity at state 2 after a displacement s. But since my surface is not smooth, it's a rough surface, then friction will try to oppose my motion. So in order to compute the final velocity at state 2, I should first draw the free body diagram of forces acting on my block. I have the normal reaction, and I have the weight of my block. I have, of course, the driving force P, and I have the opposing friction. And we have seen together before that whenever I have a sliding between two surfaces, I can express the friction, the kinetic friction, as mu k times the normal. So now, if I want to find the final velocity, whenever you have any problem, initial position, final position, and you have to find, let's say, one of the velocities is unknown, think about the work and energy principle. It's true that you can still apply chapter 12 and 13. It's not wrong, but it will take more time. Why? If you want to use your knowledge of chapter 12 and 13 to solve this problem, what is the method you will use? If I give you the same problem, but solve it using chapters 12 and 13, what will you find first?
Sum of forces equals to MA to get acceleration, then
Very good, very good. You need to first do sum of forces equal MA. You get your acceleration. Here, your acceleration will be constant because all your forces are constant. And you say, since A is constant, then I can apply the formula for constant acceleration. So let us do it together to remind you. So we do first sum of forces along direction of motion equals to MA. What are the forces along this direction? P is in the positive direction, so plus P. F is opposing motion, so it's minus mu Kn equals to MA. Now, to be able to get the expression of A, we need to find N. What should we do to find N?
We need to get friction.
No, we need to, no, to get friction, we need N. How we can calculate N in this problem?
From W لأن
Yes, very good, from W. Because if you take along, do you have any motion along Y? This is sum of X. You only have motion along X, no motion along Y. So the second Newton relation you can write is that sum of Y equals to 0. And if I project along Y, if I take Y axis positive upward, I have plus N minus W equals to 0. So my normal is just equal to the weight. And now, since I obtained the value of my normal, I can replace here to get A. So I can say that A is equal to P minus mu K times mg, which is the weight, over m. So since P is constant, and I can consider that this is a constant, because I have no force that is variable here. Since A is constant, what I can say now, to get V2, because I know the displacement delta S, which is equal to S, I can just apply between state 1 and 2 and say that V2 squared minus V1 squared equals to 2a times delta s, which is s. So 2 times acceleration times s. I know now a. I know the displacement s. I have the initial velocity. So I get my v2. But I needed 2 equations to perform this. Actually 3. The first equation is to get n. The second equation is to get a. And the third equation is to get v. When you use work and energy, you just need 2 equations. One to get n and just one to get your final velocity. Because you can say that if I apply the principle of work and energy here, the normal and the weight are perpendicular to motion, so they will not produce any work. I just have the work of P and the work of friction. So let me apply my theorem. My theorem states that the initial kinetic energy, which is known because V1 is given, is half mv1 squared. Plus, I should consider sum of work of all forces acting on my system between state 1 and state 2. If I look at my free body diagram, W and N have no work, so I have only the work of P and F. For P is a projection is I don't have to project because it's already collinear with motion and it is acting in the positive direction of motion, so it has a positive work. So the work of P is plus P times the displacement. No need to integrate because this is a constant. So I can just say that the work is the force times displacement. Now, what about the friction? The friction is opposing motion, so it has a negative work. And also it's a constant force, so I have to multiply the friction force by the displacement. And then this will be equal to half mv2 squared. The only unknown is v2. I get v2. But of course, to get n, I need also to apply sum of y equals 0. And then I apply that n is mg. So I am ready to calculate v2. So this method is relatively easier because instead of writing 2 additional equations, I just need 1 additional equation. Any question on this? Okay. Let us do a small problem to practice more on this. We have a 15.5 kilonewton car is traveling down the 10 degrees inclined rod at a speed of 6 meters per second. If the driver jams on the brakes, causing his wheels to lock, determine how far as his tires skid on the road. The coefficient of the kinetic friction between the wheels and the rod is mu k equals to 0.5. So first, let me put all inputs on my figure. What do I know in this problem? I have the value of, so this is my weight. W is given. I have the initial speed. V initial is given. V at state 1. I know the inclination of my rod. I have that now I did an action on the brakes. This means that I'm decelerating. So my velocity will be reduced, okay? Now they want me to determine what is the total distance traveled before my car will stop, okay? So when they say determine how far the tires will skid on the road, so I need to determine at the final state, I know that my car will stop under the effect of the braking.
So V equals 0.
V2 is 0. Now, what is my unknown? My unknown is the distance traveled. So whenever you want to relate displacement to velocity, think about work and energy. Because I know V initial, V1 is known. I know V final, V2 is 0. But the only unknown is the displacement. So this is a typical problem where I can use work and energy. Okay. Now, to be able to use work and energy, I should draw the free body diagram and determine what is the work of my forces. Let us plot the different forces acting on my car. I have the weight. I have the normal. And what also here? What is the additional force I have? Due to braking effect, friction will oppose motion. And they gave me that the kinetic friction coefficient is given for me. It's mu k equals 0.5. So if I illustrate friction, it will be opposing my motion because my wheels will slide on the rod. So this is my friction here. It's a we said already for a car, the friction can be driving or opposing. Here it's an opposing force to translation because my wheels are locked. When we say the wheels are locked, they are not rotating anymore. They will just slide on the rod. So the friction is equal to mu k times. Once I present the forces acting on my system, then the next step will just be to find the work of each force. Function of the displacement, of course, because the displacement is unknown. To start with, as usual, the normal has no work since perpendicular to motion here. I just have the work of the weight and the work of the friction. Now for the weight here, because I'm moving downward, I expect that the weight will do a positive work. This is why when you are moving down, it's more difficult to stop your car because the weight will help downward motion. So friction should be much higher, okay, to oppose this effect. So now, first, the work of weight will be positive because if I project my weight, it will have a downward projection. And the projection, as usual, is W sine of this angle. This angle is 10 degrees. So you can say that the work of the weight here is plus mg times sine 10 times the displacement. The displacement is unknown. I will just put the weight, work of weight function of s, so it's times s. Now I still have to compute the work of friction. The friction is opposing motion, so it's a negative work. So now for the work of friction, work of F, it's minus, because it's a constant force, since all my forces here are constant, because the weight is constant, and then the normal will be constant, and also the friction. So it's minus mu kn times the displacement, S. To be able to complete my system, my equations, I just need to know what is n, what is the value of n. So all I have to do, like in the previous problem, I should project along y, because no motion along y. This is y direction. I don't have motion along y, so I can write that sum of y is equal to 0. The normal reaction is along y because it's perpendicular to the incline, while your weight will have a projection on y. Okay, your weight is vertical and y is perpendicular to the incline here, because we considered x along the incline and y perpendicular to the incline. So if you project the weight on the incline, it's a negative projection, and you just have to multiply by cosine 10. So you get plus the normal minus w cosine 10 equals to 0. This will give you the value of your normal, n is equal to w cosine 10. And now, once you determine the value of n, you can replace back into the work of the friction. And what is the only remaining unknown? S. So now all we have to do is to apply the principle of work and energy between positions 1 and 2. Okay, so we know that T1 represents the kinetic energy at state 1. We have already the initial velocity, so all we have to do is to write half mv1 squared plus sum of work of external forces. We have determined together the work of the weight, which is positive, and the work of the normal, which is negative, and both are function of s. This is equal to the final kinetic energy, which is 0, because I have to stop my car at the final state. So as you can see here, the only unknown in the principle of work and energy will be the displacement of your car. So you can calculate the value of s. So this is the distance needed for the car to stop. Also here, you could have solved this problem using 12 answers, chapters 12 and 13, same methodology. You can find first what is A from sum of x equals max. Once you get A, you say, since all forces are constant, A is constant, so I can apply V2 square minus V1 square equals to 2A times S. And since the only unknown is S because V2, V1 are given, and I calculated A, you can get S. So always you can use several chapters to solve the same problem, but here it is easier because you need one equation in addition to sum of y equals 0 instead of 2. Any question on this? Okay,
Yes,
thank
Professor,
you.
one question.
Yes, tell me.
For the second method to calculate A, sum of forces, right?
Yes.
Okay.
Sum of forces along which direction? Direction of motion. Okay. So if you go back to this figure, to get A, you don't have motion along perpendicular to the incline. You just have motion along the incline. Okay.
Yes.
So when you
Okay.
project along the incline, you have the following. You have we already said that you have the weight, and you have the normal. The normal has no projection along motion. You just have the projection of weight and the projection of friction. And we already have determined what are these projections. So you have plus W sine 10 and minus your friction. So minus mu Kn equals to Ma. From sum of forces along Y equal to 0 at N is W cosine 10. So you can get your acceleration. Okay? You can get A and then use V square final minus V square initial equals to 2A times S. You get S.
Thank you.
You're welcome. Any other question on this? Thank you for your time. Bye.